Welcome to the classroom. Today we're talking about groundwater and the spring melt. As you probably have seen, water levels in creeks near you and even the ditches, the water level fluctuates as we get rainfall. So we get a lot of rainfall, the water flows down from the river valleys into the creeks, collects, the water in the level in the creek rises, and actually is elevated for a few more days after a rainfall event. And that's because we have a watershed. All along River Valley and further upstream, there's many contributing creeks that collect all that water from a rainfall event, and it takes time to flow down through the system. But we also have water that collects in the ground. So the groundwater level also rises, and it takes time for that water to drain, and even more time than actually the surface runoff takes to get to the creek and down the creek. So that groundwater, especially in the spring, we have collected a lot of frost that is frozen groundwater. All that space, that void space in the ground, in the soil, or in the rock gets frozen in the wintertime down a certain depth. And we call that the frost depth. That layer of frost in the spring takes a lot longer to melt than the surface snow takes to melt. And so that means that the groundwater table in the spring is elevated for quite a long time after the snow melts and after a rainfall event. So we can actually see that in places where the water is exposed. And we'll go see along the path here other locations where we have ponded surface water, but I also think there is some underground water that's seeping out of the slope. And this can be an indication of changes in soil or rock type. Different types of rock and soil have different levels of permeability, the amount of water that can be stored and flow through that soil or rock. We call that an aquifer. Highly fractured bedrock or a limestone or a sandstone that may have lots of void spaces in them. Now, if you have a very low fractured granite rock, or you have a clay stone, shale, small grain size soils like silts and clays also have a low permeability. That means that the groundwater cannot flow through them very easily, and we call those aquitards. The aquitard can actually protect the aquifer underneath from getting contaminants from the ground surface, and it can also preserve the quality of that groundwater, because it takes a long time for contaminants to travel through that aquitard, that protective low permeability layer. And that also contributes to the groundwater levels and the creek levels as the water is flowing from the surface and from the underground to our low points in our water cycle and our topography. So geology plays an important role in the water cycle and in our hydrogeological system here, which includes the creek, which includes the river valleys and all that catchment. We call it the watershed area, where the water is being collected on the surface down to our creek in this example. So let's go have a look in the forest here along the path at some locations where the water is seeping out of the ground, and it could be contributing for frost melt as well as ponded water that's flowing along the surface. Let's go have a closer look. So in the forest here, we've got some ponded water, and then it's flowing across the path, and we have some ponded water on the side. So here you can see a lot of water ponding on the edge of the path. We've got a low point at the bottom of the slope that's coming down, collecting water after a rainfall event, but I also think there's a lot of water stored in the slope there itself, and that's contributing then to this ponding water here. You can see it's running down the path, and you can see we got the slope, all right? There's no real ponded water behind, but we've got water collecting on the corner here, and you can really see a lot of water sort of flowing down, collecting in the corner, but it's also coming out of the slope. All right, and you got more water over here ponding up, but eventually not all of that water can cross the path. It's either going to evaporate or flow underground. This is a location where the groundwater at the current level is meeting the surface, and then the water it's more easy for it to flow across the surface. That could be because we still have frost in the ground here, or that the groundwater elevation is elevated because of the spring melt.
And so later in the spring, the ground will dry up, the groundwater level will reduce, and then the water won't pool here because the water level in the ground has reduced, and that way it's actually flowing underground down to the creek. Even though it's been a few days since we've had rain, there's still lots of moisture in the soil around the path, and it takes a long time for that water to evaporate or flow underground and down to all our low points within our watershed and then contribute to the creek water flow. So there you have it, a good example of spring melt contributing to groundwater elevation rise as well as surface water flow down towards the creek. And both things contribute to fluctuations in the creek level that we see many days, even weeks after a heavy rain, or many days after the snow has entirely melted away. So that's the geological aspect. And then what's the engineering link? We need to design our hydrogeological systems, our creeks and our bridges, and everything that is interacting with the hydrogeological system to be able to handle that volume of a spring melt water runoff, as well as then large storm events. And that is the engineering link.